Morning. There's calculus. It's super early at my house this morning, but the house is quiet. So we're going to record a lesson on implicit differentiation 3.8. I know we did this lesson in class. However, it was that last Friday before we left. Things were kind of crazy, and now lots of you are absent. I did put an assignment due in quarter 3. That's okay. Just submit the best you can for that one. That's fine. But I'm going to reteach it now, and then you'll have a worksheet to actually try for the assignment for quarter 4. So I'm going to go over the notes again. Let me switch this around. Here we go. So this is in the new yellow packet. Looks like this. I think a lot of you have it. If you do not, you can just download and print it out. I'll make sure it's there in Google Classroom. You can print it out. So we have implicit differentiation. We've had functions that we've differentiated explicitly as y equals f of x. If the equation can be defined in y equals f of x, you can find the derivative, or if it cannot, rather, I think that should say, you can find the derivative of each side. For example, the derivative of y squared is 2y, and the derivative of x is 1. But when we take the derivative of y, and this is the new part for today, you follow it up with dy dx. And then to solve for dy dx, you divide both sides by 2y. So dy over dx is equal to 1 over 2y. Give me a quick sec right here. All right, so we're back. But this doesn't look like what we're used to. So I want to show you that this works another way as well. If we have y squared equals x, you can actually solve this one for y. That's not always the case with implicit differentiation, but we can here. So you can find the square root of both sides. So this becomes y, a square root of x, but we write square root of x as x to the 1/2. So x to the 1/2. Now when we take the derivative the old way, we get dy dx equals 1/2 x to the negative 1/2. Well, this is a negative exponent, so if I slide it to the bottom, this is 1 over 2x to the 1/2. This should be a square root. Well, these two should be the same thing, right? Look up here. They are. 1 over 2y. So you do wind up with the same result. Now, this one was lucky. You could solve in terms of y. When we get down to some of the other problems, that's not always the case. So rules for implicit differentiation. All previous derivative rules apply. And what do I mean by that? I mean everything on your golden ticket. Ta-da, everything here. No, mine's blank. Yours is mostly filled out. Everything on your golden ticket, all those previous rules still apply. Second thing, when finding the derivative of y, follow with dy dx. That was the part where we wrote dy dx right afterwards, right up here, that guy. And then finally, the last piece is to solve for dy over dx. Now, I like example 2. I think it's a nice way to illustrate that. In the first one, we couldn't solve for, or we could solve for y. In this one, we cannot. So what we'll do is find the derivative of each piece. The derivative of 5y squared is 10y dy dx. The derivative of the sine of y, check your golden ticket, is cosine of y dy dx. And the derivative of x squared is 2x. So this dy dx piece, that's the new part. Now, what we're going to do, and this is the part that students are often a little bit rusty on, is to solve for dy over dx, we're going to factor it to the front. So this becomes 10y plus cosine y equals 2x. And from that point, to get dy over dx by itself, we divide one more step. And that is the answer to your derivative. That's the first derivative. So these answers look a little bit different because you'll have a y left in them, and that's completely fine. Not a problem at all. All right, next page. Second derivative, we'll do that. I think we did this in class. We did example 4 first. Whoops. Sorry, document camera issues. All right, so example 4, find the tangent and the normal line. The tangent line is what we've been doing. That's the line that's parallel to our curve at a particular point. So this one's parallel. Or I guess it only touches in one place. Parallel is probably not the best word. But normal is perpendicular to the tangent line. We don't use that very often, but it's good review. So we need to find the derivative. X squared, the derivative is 2x. Now this minus xy, this is really being multiplied. We have to use a product rule. So it's the first times the derivative of the second, and the derivative of y is 1 dy dx, plus the second, which is your y, times the derivative of first, the derivative of x is -1, isn't that negative, plus the derivative of y squared is 2y dy dx. And then a lot of students get all the way to the end, and the derivative of 7, they forget, the derivative of 7 is 0. So here we go. Long, long, long implicit differentiation. All of this, as a reminder, was your product rule. For that x times y piece, that negative xy. So all of this is the product rule. What we're going to do is get dy dx on one side and everything else on the other. So the negative x dy dx and the 2y dy dx stay. And we have to move this 2x to the right, so negative 2x to the right, and negative y move to the right. Hold on. Never a dull moment around here. All right, so we have left dy dx on the left, moved everything else over to the right. Just like the last example, you're going to factor out dy dx. Negative x plus 2y is equal to negative 2x plus y. Divide by what's left over. Dy dx is equal to negative 2x plus y over negative x plus 2y. Now, that gives us the derivative, but to find the equational line, we need the slope. So if you recall from class, we have to substitute -1 and 2 into the derivative. So the slope of the tangent line is going to be dy dx when x equals -1 and y equals 2. So this is -2 times -1 plus 2 over negative of a -1. Oh, we got lost. Plus 2 times 2. So in the numerator, I've got 2 plus 2, this is 4. The denominator, this is going to be a 5. So in class, I'd said point slope form is completely acceptable. Let's keep that up because that's easier. And I've run out of space. So tangent line is going to be y minus 2 is equal to 4/5 x minus a -1. So this would really be x plus 1. Your normal line, remember that's perpendicular, everything stays the same except for the slope. And to come up with a perpendicular slope, you did that in Algebra 1 and Algebra 2, but it's been a long, long time. So 4/5 for your slope, your perpendicular is the opposite reciprocal, so -5/4. There you go, so your tangent and normal line. Now, you could distribute the slope and solve for y, that's completely fine. But I'm perfectly happy with point slope form. So slide back up here to example 3. The piece with the second derivative. Wish that were a little bit more clear. All right, so implicit differentiation. You want to find the first derivative just like we did in the previous examples. So this becomes 6x squared minus 6y dy dx, and the derivative of 8 is 0. Now, I would like to solve for dy over dx. I'm going to subtract this. Negative 6y dy dx is equal to negative 6x squared. Divide both sides by negative 6y. Dy dx is equal to, those both cancel out, x squared over y. Awesome. Now, that's only halfway there. We have to find the second derivative. The second derivative means the derivative of the first derivative. Now, these are being divided, so if we've got division, that's our quotient rule. So it's the bottom, which is y, the derivative of the top, 2x, minus the top over the derivative of the bottom, and that's 1. And the new part for today, dy dx, all over y squared. Now I'm going to clean this up just a little bit before we talk about the next step. So y2x is 2xy minus x squared dy dx, all over y squared. Now it looks pretty good, but there's one problem with it, and that's the dy over dx. In all of your science classes and English classes, when you had vocabulary that you had to define, you were never ever allowed to use the word that you were defining in the definition. Can't do that. It's kind of what's happening here. You have the second derivative defined in terms of the first. That's not going to work. So you have to replace it with the first derivative. So d squared y dx is equal to 2xy minus x squared over y, all over y squared. Well, we took care of the notation problem. The dy dx is out of here. But the next problem I have is an algebra problem, and that's that y that's in the denominator of the numerator, this one. That's no good. So what we need to do is multiply everything by super common denominator, and that's y. We've done this in class, especially with those limit problems. So y over y is 1. We're allowed to do that. I'm going to distribute this all the way through. So this y over here becomes 2xy squared. This y with this set, well, those y's cancel out. And now I just have x squared times x squared, which is x to the fourth. Y squared times y in the denominator becomes y cubed. That is your second derivative. Now, it didn't happen with this example so much, but every once in a while you can factor something out of the numerator and it will cancel with the denominator. And then even every once in a while, something can factor out of the top. Sometimes you can substitute the original problem back in. I think we did that when we did this worksheet in class. I remember we did most of this together in class. You don't have to redo this one, but I did upload a secondary worksheet. So if you have the, oh, this silly camera. If you have the ability to print that out, that might be easier. You can work on just a piece of notebook paper and upload your work. That's totally, totally fine as well. If you are into your iPad and you want to mark up a PDF for it, totally fine. But remember, we're going to change the scoring rubric on these a little bit. These are each going to be worth 6 points. You have 3 points kind of for your accuracy and 3 points for completion. So make sure you're doing your best on these. We're not really going to have tests or quizzes in the traditional sense, so I need a few more points in other places. And that's what I have for this lesson. So I will make another recording for inverse trig functions, and this will be coming up hopefully sometime today, Monday. These are more formulas for your golden ticket, and they're not really, really too bad, but they're just a little bit more to use. So there you go.